for it. Okay, all right. So our speaker today is Guillermo Contreras, and he got his PhD at Dortmund University, stationed in Hamburg at DESY, working in the H1 collaboration at HERA. He then moved to Sinvestav in Mexico, creating a small group to continue working in H1. And then in 2001, he joined the ELISE collaboration and went on to the Czech Technical University in Prague in 2012 as an invited professor, where he stayed and created a group working on ELISE and related phenomenology in PQCD. So we're excited to have him today as our speaker, and I will turn the floor over to him. So Guillermo, please. Thanks.
Hi, everybody. Thanks for the invitation. And now let me know if I managed to share the screen. You should see my screen now.
Yep, looks good.
Right. Okay, so thanks for the invitation. I will talk about diffractive vector meson photoproduction from the experimental side. And I hope to convince you that even though this is a very simple process in principle, in practice, you have many possibilities to play with it. And if you have any comment or question or doubt during the talk, please let me know, because I'm not sure about if everything that I say you already know, and probably several things that I will say you will not agree, so we can discuss about them. So now this thing doesn't want to work now. Okay. So as the main focus will be in ALICE results, on ALICE results, because I work in ALICE currently, and many very relevant results will be skipped. So I apologize in advance. And just to give you an idea of what I mean with many, this is a beautiful slide from Sergey, who he presented these a few days ago in the open question meeting, from the results from H1 and Zeus from HERA, only in vector meson photoproduction. And I will show once or twice of these data in the following slides, but basically I will skip all of it. Also, I will skip many results from RIC. I will show one or two things from RIC, and I will concentrate only on vector meson photoproduction. There are many other issues that, or many other observables you can explore in photoproduction. So let's start. This you already know, but I wanted to point out a few things to have a coherent picture from the start where I want to go. So what I want to study is perturbative QCD. And it turns out that the objects that are described by QCD in the normal energies of our current time are inside the bound hadrons, are bounded in hadrons, the quarks and gluons. And perturbative QCD, what it gives me is evolution equations that describe how this structure of these hadrons changes when you change something, either the scale or the energy of the interaction that you are using to test them. And I am particularly interested in the high energy limit, where one is supposed to find this saturation region, which up to now it has not been conclusively found experimentally. So when I say what I'm interested in, instead of perturbative QCD, I would say to measure the structure of hadrons in terms of quarks and gluons at different scales and energies. And to be a bit more precise, this is what we know in a nutshell about the structure of hadrons. And here you have data from, well, not data, but PDFs extracted from data from H1 and Zeus. And you see here that the gluon dominates a small x. And you also, well, you don't see it in this particular scale, but it grows as a power law at a fixed scale. And you see here it is suppressed by a factor of 20. That means that somewhere here, you already have 0.3 times 20. So you would be somewhere there. So what I'm interested in is, to be more precise, events which are sensitive to the gluon content of hadrons, because I'm interested in what happens in this region. And that's why I want to talk to you about this type of events where you have a charged particle that comes in, emits a photon, and this photon will interact somehow with this other particle that comes here through QCD somehow. And in the process, we will get a vector meson. In this type of process, QED enters here. And there are very interesting recent developments, which I will not talk about. And then a perturbative QCD is here. So this is what we will try to get out of this type of measurements. And this process is particularly interesting because here you need to have no color exchange, and that means that you are very sensitive to the gluon distribution because you need at least 2 gluons to manage to have here no color exchange. At the LHC, this object here has been a proton, a lead ion, or a xenon ion. And the center of mass energies of the photon target system that you can reach at the LHC within the experimental acceptance is about 1 TeV in photoproduction of protons and about half of it in photoproduction of lead ions. And the current measurements are based on a few hundreds to few thousand of events, but this will change hopefully soon because for run 3 and run 4 at the LHC, we expect millions or even billions of events. This is a table from a CERN yellow report, and you have different acceptances and for lead, and this is the number of events that you expect to detect in the detectors. So already with some acceptance and efficiency and everything inside. So you see, for example, for the raw, you are expecting 5 billion events. So we will have a lot more data. So what I am showing today regarding LHC results is just an appetizer. The main course is coming. Hopefully in November next year, we will get already a big chunk of these events. And I will show very little experimental details, just to give you an idea how this process look in reality. Here it is a candidate for a JEP decaying in 2 muons, and there is nothing else in the detector. You are used to these collisions of lead-lead. This is a lead-lead collision, where there are literally thousands of charged particles per unit rapidity. And in this case, you have only 2 particles. And this brings a set of problems because this accelerator and these detectors were not optimized for this type of physics. So one problem is how to trigger and select these events. And to solve this question, this question is the origin of why we have up to now just a few hundreds, few thousand of events. And the solution, an answer of this question, at least in Alice with continuous readout, is what it will give us these millions and billions of events. And then there is another open question that this is not so clear, and I will come to this later on, is how to ensure that there is nothing else. And this is the only thing that I will talk about experimental details. So let's start then with the physics. And let's start with the rapidity dependence. So you have here a scattering angle that gives you rapidity. And through this formula, the rapidity gives you an evolution in X. And as I told you, I am interested in the small X limit and how the structure changes with X. And what you expect is that the gluon, as you know, the gluon distribution rises as a power law. I just show you the plot about it with decreasing X. So you expect that the cross section will rise also as a power law, because in first approximation, it goes like the gluon distribution is square. And then you hope that at some point it will saturate. So this is what we have up to now. What you see here is the cross section for the photoproduction of JEP of protons. Here is the cross section. Sorry, This is as a function of the center of mass energy, and this is a function of X. And you see that in the same detector, all these are the red and black points that cover all this area. We cover with the same detector about 3 orders of magnitude in X up to now, and we hope to cover more later on. The cross-section grows as a power law. This gray band is a power law fit to the data, only to Alice data. And all type of models describe data. You have here models based on vector dominance model, on DGLAP equation, on BFKL, on color, glass, condensate, picture. So everything describes more or less data. So one question that is still open is, where is saturation? Is it that is observable is not strong enough to look for it, or it is just that our precision is not that good, or that saturation is somewhere outside the reach of LHC? So let's try to look at a different way to look for saturation, to see if in another observable we can find saturation. And you have seen this diagram where you see the case for nuclei. And basically, the bottom line is saturation expected to set in earlier in heavier nuclei. So let's look at the same process, but in heavier nuclei. Specifically, we can look at it in lead-lead. Here now you have the cross-section for the coherent production of GEPSI in lead-lead collisions as a function of rapidity. And here you have the data and a bunch of models. So first, I would like you to look at this light blue band, which is called the impulse approximation. And this corresponds basically at scaling the results of the same process of protons to the case of lead ions, conserving only the coherence of the interaction, so that the lead acts as one entity. And with that, you can define some nuclear suppression factor that for X about 10 to the minus 3 that corresponds to this rapidity, you have a suppression of 35 to 40%. Another thing that you can see from here is that no model really describe data. Some models do well here, some models do well here, some models do well here, but no models describe all over the place. So there are two open questions here. Some of these models are based on the color glass condensate ideas or BK equation, but some models are based on ideas of saturation. And at least to me, it is not clear how much is just a different language and how much are different physics issues. So it is, for me, it would be interesting to know if the theoreticians could come up with an observable that would allow us to separate the different ingredients that go here, so that we know how much of shadowing is saturation and how much is something else. But still, the question is if there is saturation in this data. So what about trying to plot it against X? The problem is that you have an ambiguity because you have two sources. So you can have that this ion is the one emitting the photon, or this guy is the one emitting the photon. And as you have two sources, you have two values of X. And here you see more or less what happens. Points here have about 95% of the cross-section for the large X contribution, and about 5% for the low X contribution. When you come around here, you go to 60-40, and then at mid rapidity, per definition, you have exactly half and half. So how to disentangle these two contributions so that we can extract both the low energy and the high energy contribution? In principle, you need another independent measurement at the same rapidity, so that you have two measurements for two observables, and then you can find them. Up to now, there are two proposals how to do this. One is to measure the same process in peripheral collisions, not ultra peripheral collisions. That is what we have been showing up to now. And the other is to measure the same process when the process is accompanied by electromagnetic dissociation. And both options select different regions of the impact parameter, and I will discuss them now. First, let's start with peripheral collisions. What you have here is a measurement of ALICE of this RAA that I guess all of you know. And here you have the centrality of the collisions. So these are very central head-on lead collisions, and these are very peripheral collisions. And roughly speaking, for these peripheral collisions, you expect to get something about 1 here, roughly 1. And you see 3 colors. The black are GEPSI producing with a PT between 1 and 8 GeV, the blue between 0.3 and 1 GeV, and the red between 0 and 0.3 GeV, so very low PT. And you see that the red is not 1, it's really far, far away from 1. And the way to interpret this is that this is the contribution from coherent photoproduction processes. Why? Because in coherent processes, you have a relation between the transverse momentum of the GEPSI and the size of the target hadron. And this relation is inverse. The proportionality is one is inverse to the other. So as the target hadron lead in this case is pretty large, we expect very low PT. And this you can see in this other plot. You have the PT distribution of these events. And you have here the data that when you go to 0, tend to go down as you expect because you are running out of phase space and suddenly shoot up. And you compare that with a coherent photoproduction GEPSI according to a Monte Carlo model from Starlight. And you see that this is quite compatible. So that means that we have measurements with a small impact parameter and with large impact parameters, so independent measurements at the same rapidity, and we can then extract both contributions. And I have attempted to do that in this paper, where you have again a X here and the center of mass energy here. This is the point at mid rapidity, and these are extreme points at forward rapidity that you can disentangle one large X and one small X contribution. And just to be provocative, I ask again the question, what is saturation? And you expect again a power law behavior that at some point saturates. And a power law in this scale, which is log-log, is a line. And I put this line not to convince you that we are seeing saturation because the error bars are very big, but to point out again that we are expecting millions or hundred thousands of GEPSI. So we will be able to put here several points. I don't know how many, but let's say 7, 8 points all along here with relatively small error bars. So this is very promising. Another option to disentangle the low energy and high energy contributions was proposed in this paper, and that is to use electromagnetic dissociation. The electromagnetic field of these guys, if these are heavy ions, is very, very, very strong. So there is a probability that these two guys who interchange this photon to produce the vector meson exchange another photon, and this photon excites this nuclei, and upon the excitation, you get a neutron with very, very low energy in the rest frame. And that means that it will be boosted in RIC or the LIC to very large rapidities along the beamline. And along the beamline, we have these 0-degree calorimeters, which are designed to measure precisely these neutrons. And here you have a result from ALICE, where we have 0-degree calorimeters in both sides for this beam and for this beam. You have here one of them and the other here. And this yellow point is when you measure nothing, so 0 neutrons in either side. This is when you measure 1 neutron in one side and 0 in the other, and 0, 1, and so on. And here you measure 2 and 2, and so on. So you can make classes of events with a vector meson and no forward neutrons, or only neutrons in one side or neutrons in the other, in both sides. And why you want to do that? Because you choose different impact parameters. Here you have the prediction from a new Monte Carlo Nuno, which basically produce to you event by event these neutrons. And here you see the probability of producing, of having this type of events for the different classes. So in black is 0n, 0n, so no neutrons. In blue is neutrons only one side, and in red in both sides. And this is the impact parameter. And you see this red curve is really peaked at low impact parameters, while the 0n, 0n is peaked at very high impact parameters. The bad or the not so nice feature of this is, as you see, the color scale is logarithmic. We have very few events here. So JEPSI is not the best option to look for it at the first time. So we can go and move something else in this diagram. And now what I will move is I will look for a different vector meson. So I will change the mass of the vector meson, and I will lower the scale of the process. Why? Because first saturation is expected to appear at lower scales. It is expected to appear earlier at lower scales. By the way, at the EIC, you will be able to do these continuously by varying the virtuality of this guy. You have to be careful that if the scale is too low, perturbative QCD may not be applicable anymore. So you go to, if you are lucky, to a semi-hard scale, or you can study the approach to the practice limit of QCD. And at low scales, the good thing is that the cross-section is a lot larger. So you have more events available. So what we did to test this case of electromagnetic dissociation is we measured the photoproduction of rho in coherent photoproduction in different classes, 0n, 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 xn, 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 at mid rapidity, so around 0 rapidity. And what you see is that in the three cases, the models more or less follow the data. So within 1 sigma, they more or less follow the data. So the idea seems to work. And the measurements at mid rapidity are very good to do this test because you don't need the separation because both contributions are equal. So you don't need to disentangle anything, both of them are equal. So you can test very well this type of new ideas here. As it seems to work, now we are working on trying to do the same with JEPSI with using run-to data, so data that we already have. And then we will do it using the new data next year, hopefully. Let me make a comment here, and it is the only experimental comment I will do, is that, as I told you, we will get a lot of data, hopefully. That means that the precision of the measurement will really go to the percent level. And then you have to care a lot more about many other things. And one of the things you have to care about is the implementation of the exclusivity condition so that you know that this is really a coherent process. And to use the same detector to measure ultra-peripheral collisions, these processes, these events that have only 2 tracks, and head-on lead-lead collisions that have thousands and thousands of tracks, jeopardize the single track efficiency. Simply the detectors do not have the dynamic range for it. So the separation between, let's say, peripheral and UPC events get complicated. Then the precision that we will get is increased partially because we will have a lot more of events. And that means that we will have more pileup also. So different events will be detected at the same time by our detector. And the other issue that I want to mention here is that electromagnetic dissociation also produces charged particles, and they produce more charged particles for these XN type of events. So the activity vetos, the vetos that you use, or the conditions, criteria that you use to say that the event is empty, may have an inefficiency that you have to determine. And this is illustrated in this nice slide from Igor. where you see here the energy of the photon in the rest frame of the nucleus, and you see the cross-section of this photon with the nuclei for lead, and you have at few MeVs, the giant dipole resonance, but then you have this quasi-deuteron absorption, which already produces a proton, and then you have the delta or the multiple pions. And this type of effects, depending what type of veto you apply, may account for a sizable effect, for 10, 15, 20%. So suddenly these type of measurements, which are very clean, are not so clean, and one has to, if one really wants to go to very, very precise measurements, one has to take into account many, many details. Okay, let's go back to physics, pure physics. Once we have the raw, then we can also try to look how it looks like when we look at scatter of protons. And this you can do in proton lead, because in proton lead collision, the lead is the guy who will emit the photon, normally in most of the cases. So you have photoproduction of protons. And you have here data from CMS. Here is the center of mass energy. Here is the cross-section for the photoproduction of the raw meson. And the red points are from CMS, and the other points are here from HERA and here from fixed target experiments. Up to now, we cover similar energy range as HERA. You see the cross-section is slowly growing. For round 3 and 4, LHCb and ALICE may be able to measure this somewhere here. It is not 100% clear to me that this will be possible, but it may. So here is rising, no signal of saturation. So let's do again the same trick, and let's go and look how it looks for lead. So here again you have the same data I showed a few slides before, but now not separated in different classes, but all together. And the first thing that you see is that this is a huge cross section. Yeah, this is almost 1 barn, so half a barn. We have measurements at mid rapidity, so we have no ambiguity, and we can go from the lead cross-section to the gamma lead cross-section. And this was done here by Joachim. This is a very nice plot that he sent to me a few years ago, where he put in the same picture the results of photoproduction of protons and of lead. And you see here that the slope is different here and here. So one question is, have we reached the Black-Disk limit in this case? Well, to answer that, we could try to move another thing in this diagram. So let me move now this guy here. And instead of using lead, let's use something else. And what you expect is that there is a different dependence on A for pure nuclear form factor, so no saturation, no nothing, and the Black-Disk limit. Note that for EIC, you will be able to study many, many different nuclei, which is not the case for LHC. But anyway, we went and did a measurement with xenon. You see it here. And we put it together with our measurement of lead and took data from H1, very recent, very precise data from H1 of protons. So we have three points, and we compare these 3 points with the models and with the expectations. All these 3 points are at the same fixed center of mass energy. And this expectation here is what you would get from just coherence, just the form factor. This one here is just the geometry of a Black-Disk limit. And these guys here are models. The red one is based on some kind of shadowing. And this blue one is based on the color dipole model, including hotspots and some saturation prescription. So we have not reached the Black-Disk limit according to this plot, but this plot already tells you that such a measurement can have a big potential. Let's move now to something different. Up to now, we have been studying this variable, which is the longitudinal degree of freedom. But now let's look at this variable, which is a window to the transverse structure. The structure in the transverse plane to the movement of this guy. And what you expect is the distribution of gluons in the transverse plane will be sensitive to different saturations effect that if you just look at the longitudinal component. So here you have some recent data from Alice about JEPSI photoproduction at mid rapidity, where you have here the signals for this point and for this point, and you see beautiful peaks, very clean measurement. And this is the photoproduction as a function of T, the Mandelstam variable. And you compare the data to different models. This model here is based basically on the form factor and I do not describe the data. Here you have the ratio of model to data, and the blue one is this point, and it not only do not describe data, but the description depends on T, or the lack of description depends on T. Then you have a shadowing-based model and a BK computation, which are relatively close to data. And if you would see these with a big zoom, with the current precision, both of them more or less describe data equally, but the T dependence is different for both models. So again, how much of shadowing is saturation? Because one model is based on shadowing, the other is saturation. And apparently the answer depends a little bit on T. So this is another promising avenue to study. And this measurement is cut at relatively low T, because here we have incoherent events that then will dominate the cross-section, and then it will be difficult to separate both contributions. So one question is how to reach a larger T. One hope is that we can use events of 0n, 0n, so without neutrons, because incoherent production normally is accompanied by neutrons. So this should suppress incoherent production. So let's go and look now at incoherent production. Incoherent production is very interesting because in a Wood-Walker approach, it is sensitive to fluctuation of quantum fields. So the structure of this guy changes event by event. This is a quantum object. And the variance of these changes is, you can measure that with incoherent photoproduction. And what you expect or hope is that the variance of the fluctuations provides new signals of saturation. Up to now, there are very few data. You have here one measurement from Alice compared to 3 models. And none of the models describe data, but it is fair to say that there is large uncertainty both in the models and in the data. The models can be moved up and down, at least, for example, this model can be moved for this, changing, for example, the prescription for the wave function of the JEPSI. We are analyzing new data, so maybe we have soon some new information about this. And one thing that we want to explore is how much can we learn from the T dependence. So here you have the cross-section for coherent, these guys who are going here, and for the incoherent production. And as I told you, the other measurement, we cut it here because later on, the data is dominated by incoherent production. But you have 2 models of incoherent production, one where you have fluctuations only at the nucleon level, so the degrees of freedom are the nucleons in the nuclei. And in this red line, you have subnucleonic fluctuations. And you see there is a difference in the T dependence. This is one model, but other models will give you the same behavior here. This difference is relatively large. You see this is a logarithmic scale. As I said, maybe we can get around the problem of normalization just looking at the T dependence, but anyway, it would be interesting if we could constrain the knowledge of the wave function. And one way to do that is to use excited states, because the process is very similar, and the only thing that you are changing is the wave function of the vector meson. And what you expect is that the angular momentum structure of the wave function may enhance or suppress some of the effects that we are looking for. Here you see some recent data from Alice for psi-2s photoproduction at mid rapidity. We have only one measurement. And you have it again compared to this nuclear suppression factor, to this impulse approximation. And we have the same nuclear suppression factor as found for JEP-psi. But interestingly, some of the models that describe the JEP-psi cross-section do not describe the psi-2s cross-section so well. For example, this green line describes both measurements, but this red line do not. It describes the JEP-psi, but not the psi-2s. So there seems to be here some sensitivity. And the question is how to use this type of measurements to constrain the wave function, our knowledge of the wave function. For the EIC, you also will have the handle of Q-square dependence, which is very important in this context. And there are recent studies about that. You can have a look, for example, here at this one. Now, I am in the last few examples, and I go to something a little bit more different. And for example, you can have in this type of event some kind of transmutation. You can have events where this guy is a proton, and this guy here is a single neutron. And this process allows you to access the pion structure. This works like this, that you have your photon that somehow interacts through some diffractive process to create the raw. But this guy here interacts with a pion that comes from this vertex. So you have the proton that converts to a neutron with the exchange of a pion. And then this pion scatters elastically of this photon or raw meson. And this was measured recently by H1. And what was found is this is the photoproduction cross-section, so the total cross-section of the gamma of the proton as a function of the center of mass energy. And this process, in this case, the cross-section is decreasing. But you can also extract then the cross-section of the scattering of the photon of pions. And in this case, the cross-section is constant. This kind of processes are very, very interesting and are, in my opinion, are interesting both for LAC, but there we have the problems that in many of our data taking periods involving protons, the CDCs, the 0 degrees calorimeters are turned off to preserve them because they are kind of delicate. But in EIC, you may want to explore this kind of processes. Now, what else can you do? You have these vector mesons in a very, very clean environment, so you can look for new states. And as the environment is so clean, you expect that you can spot them and confirm them without so much problems. One example is here. You see pion pairs in lead-lead collisions seen by Alice. You see here the mass distribution. These are ultra-peripheral events, so you have only these two pions. This is the mass above the rod. And here you have the PT distribution for the events around this bump. And you see the PT distribution is typically for of what you expect of coherent photoproduction is peaked at very low PT. And this kind of bump has been seen in the past also by H1 and by STAR in a similar position, but the parameters are not 100% equal. And also, okay, we hope that with new data, we can look at these with more detail. And of course, these should be available, accessible also at the EIC. Another example, just to show that there is life outside Alice and a very vibrant life, is this nice measurement by STAR, where they look for 4 pions in ultraperipheral collision. So you have only 4 pions, nothing else. And you can separate these 4 pions in 2 pairs. And you see here the mass distribution of these 2 pairs. And this looks really like a row, and this looks like something else. So the mass of the pairs is compatible with a decay to a row and an F0. And using this assumption, you can measure this kind of events. Here you have the invariant mass of these 4 pions. The data using this measurement, it was, you see, very large statistical errors. So it's not clear how many resonances are here. If you get really hundred thousands of events, then we could do even a partial wave analysis and really disentangle what is in here. And of course, such a thing should also be accessible at electron-ion colliders. Another topic is that you can study basic quantum mechanics, because at the RIC and at the LIC, but not at the EIC, you have 2 potential contributors, so you have an interference. And what you expect is that the interference is more important than mid rapidity, where both amplitudes contribute more numerically the same, but at the low PT. So this was also measured by star in the raw photoproduction. You have here the T variable, the Mandelstam T, and the yield as a function of T, the mid rapidity more or less. And what you see here is a drop, which is interpreted as destructive interference, which is what you expected to see and what you see in the data. In principle, this should also be visible for the JEP side, but probably we would need more data. So probably this will have to be done in round 3 and 4. This could be a good tool to understand better peripheral events. And there is this very nice paper where they use JEP side photoproduction and azimuthal asymmetries and interference to try to disentangle the different contributions to peripheral coherent photoproduction processes. So I'm reaching the end of my talk. So instead of a summary, let me go fast over what I have told you. These diagrams, which seem relatively simple, have a lot of richness there. There are many things you can vary. You can vary the rapidity. You can vary the impact parameter of the emitted photon. You can vary the mass of the vector meson, the incoming particle. You can look at the transverse structure using the T dependence. You can look at the quantum fluctuation using coherent processes. You can study the non-perturbative aspect of the wave function of these vector mesons using excited states. You can look for new states. You can go for leading neutron events where there is this transmutation of proton and neutrons to study the pion structure. You can study quantum mechanic interference at a really small scale. And there are many things I didn't talk about just because of the time. You can study angular correlations to study spin effects, not only the spin of the vector meson, but of the interaction really. And there are recent advances that promise that you can learn several things of looking at angular correlations of these 2 objects. There are very, very interesting things going on also in experiments, for example, at JLab, where they are measuring this process at threshold when W is really very low and you have barely energy to produce the JEP psi. The theoreticians claim that you can try to understand with that the origin of the proton mass or even mechanical properties of the proton, the kind of pressures inside of the proton. So this is very interesting. And I have not even started to talk about what you can do if you use polarized beams. So everything what I've said is for unpolarized beams. So you can imagine what the richness of this once you start saying, okay, let's polarize this guy, let's polarize this guy. let's polarize them in different directions. So instead of a summary, I hope I convince you that this deceptively simple process is in reality a Swiss Army knife for QCD. And with this, I finish, and I hope you have some questions and comments.
Great. Thank you so much, Guillermo, for a really interesting talk. Do we have any questions? Please put your hands up. I see raised hands from Spencer. Go ahead.
Thank you, Guillermo. A very, very nice talk. I had a comment on slide 28.
Yes.
Yeah, so you talked about, what can we learn from the T dependence? I think that's a really interesting question. As you probably know, I spent quite some time working on that with STAR, and there were a lot of impediments. I mean, basically, yes, clearly is a T dependence. This is just essentially d sigma dt is the Fourier transform of the distribution of the interaction sites in the target. And clearly you get something different if you imagine a Wood-Saxon nucleus, i.e. no shadowing, no nothing, versus a black disk where you basically sample the whole thing equally. And you clearly expect a significant change, but it seems rather difficult to actually make quantitative measurements because you have to deal with things such like the photon PT spectrum.
Yes, indeed, but I hope that at large T, this contribution will be minimal or small with respect to this. So if you go, this ends at 0.3. There is another plot by Heike that goes to 0.7, I think, which is still reachable. And then you have a factor 10 difference. So I think the influence of the PT of the photon for T about 0.5, 0.7 will not cover a factor of 10.
Okay, so yeah, for the incoherent part.
Yeah, for the incoherent part, yes. Yeah, for the coherent part, there has been a lot of advance. You have been working on that, and many other guys. And yes, this measurement we did is a bit brave, and we'll need a lot more precision here for the interference, understand very well the interference. And there may be some component, as you say, because of the PT of the photon that we try to take into account and put here in this green band as uncertainty. But this is as we know today. Let's see what we know in a few years. Maybe either this goes smaller or maybe, I don't know. Let's see. Yeah, this is interesting, this PT. But I think the PT of the photon is more important for this kinematic range than for this one, especially that the difference that we are looking here is a factor of 5 or 10.
Okay, thank you.
Any other questions, comments? I don't see anybody else's hand up. So if not, we'll thank Guillermo again. This was very interesting. I really enjoyed it.
Okay. You're welcome.
Thank you so much. And we'll put, I got your slides, so we'll put them up on the website, and you'll get to see yourself on YouTube as well.
Okay. Thank you.
All right. Thank you so much.
Bye.
Bye, everybody.
Bye.